Today we have Gerardo Bledt. Gerardo is now a lead locomotion engineer at Aptronic. He's working on control of legged locomotion. Before that, he was a postdoc and a PhD at MIT working on data-driven and model-based control for legged robots. During his PhD, he implemented walking controllers on MIT Cheetah 3 and Mini Cheetah. So we are looking forward to your talk, Gerardo.
Great, thank you. So yeah, like you said, my name's Gerardo. I did my PhD in the biomedic robotics lab at MIT, and I'm now working as the lead locomotion engineer at Aptronic, designing control algorithms for legged systems. So today I'll be talking about generalizing, improving the regularized predictive control algorithm that I developed during my PhD. And kind of taking it a step from the stuff that I've shown in the past on Mini Cheetah and how you can generalize that to things like bipeds, humanoids with non-point feet, how to integrate vision, a bunch of stuff kind of extending from the work that I've done previously. So as an overview, I'll kind of give a quick recap on regularized predictive control, what the algorithm is, how it's related to model predictive control and how it kind of branches off of it, how it all works. And if you guys make it through that part, I promise I'll show some good robot videos. So I'll talk about the generalization and improvement to things like non-flat ground, both how to integrate vision and even how to deal with non-flat ground in a more robust way while blind. And then I'll talk about how I extended the algorithm to bipeds and humanoids, including non-point feet. A lot of the algorithm in the way that I wrote it originally kind of relied on having a point foot assumption. But you can basically extend it to any kind of feet, line contact feet, any kind of plane feet. So I'll be talking a little about that. And then I'm going to show some real-time hardware results of the nonlinear MPC controller that I made on a very simple biped robot that you see over there. So get started. So first, I kind of want to talk about the intelligence abstraction in legged robots, what I personally, how I approach the legged robot problem, and kind of the different layers that there are to like a legged robot. So the first key component I like to think of is actuation and sensing. Similar to humans or animals, you have to have good muscles, you have to have the sensors to be able to operate in your environment. And then the next level kind of up is this coordination and local state estimation. So the coordination is now that you have your actuation systems, can you get them all to move together, cooperate with each other? And also, do you know what you're actually doing? Do you know what your kinematics are? Do you know if you're touching the ground versus if you're not touching the ground, stuff like that. So if you're able to do that, the next layer up is the locomotion control. How do we leverage this coordination and state estimation to get the robot to actually move in a useful way, and how to manipulate its environment, in this case the ground, to move its body, balance itself, how to get where it needs to go. So if you're able to have the robot control itself, balance, that's all great. But without perception or any kind of environment knowledge, your robot's just going to be blindly walking around the world. So the next thing that you want to integrate is kind of this perception, and be able to know some information about the world before you actually touch the world. That way you can kind of plan paths around it. You can decide, okay, here's a stair, I know what I want to do, or here's an obstacle in front of you, I want to move around it, and how do I actually get to the goal location? if you're able to do all of that, kind of the holy grail, in my opinion, is this decision autonomy. And I don't have a good robot video for that because I personally have not implemented it, and I don't know of any robots that are able to completely decide what tasks they need to do, be able to get there, perceive them in a completely autonomous way without any kind of supervision. And that's, I think, what we're all kind of striving for, is to be able to send a robot to any kind of situation and have it able to make decisions on the right actions to take, be able to get to whatever its goal location is, and be able to manipulate its environment to actually achieve these goals. And these are just kind of the way that I think about it. There's a lot of nuances and kind of overlap between them, but this is a simple representation. So a lot of my talk is going to focus mainly on this kind of locomotion control, how to actually get the robot to manipulate its environment locally, and how to move around to be able to balance and be able to get where you need to go. So control for legged robots, I think, it's a very challenging problem. Legged robots are complex, multi-degree of freedom systems. They have discrete hybrid nature, so you're constantly coming in and out of contact. You gain and lose different control inputs as the robot picks up legs or puts them back down. And if you're doing any kind of dynamic locomotion, you're rarely ever statically stable. A lot of the work that I do is not quasi-static, so you're never really have the center of mass above your support polygon. You're kind of jumping around between them and kind of deciding where to put the foot down to be able to balance yourself next. And you also have a lot of uncertain conditions. You're traveling around rough terrain. You don't always know exactly what you're doing. It's a very highly dynamic field. So the different ways that I think that I've shown a lot of success, or at least 3 of the ways, are this heuristic control. And you can think of kind of the like Mark Raybert's work early on at the MIT Leg Lab is kind of like the Raybert heuristic and that kind of stuff. It's very useful and it's very powerful, but it requires you to have expert knowledge of the system, and it's difficult to consider every case. If you want to make a heuristic for every single possible case that your robot is ever going to encounter, it's going to get very difficult. Then the next mode that I like to think of is optimization control. And this has its set of problems too. It can be very computationally expensive, or you can have convergence issues. Sometimes you might have to simplify the model too much, or you may have to, you may not be able to run it in real time online. And the last one that's becoming especially popular nowadays is this kind of reinforcement learning control. And so the video that I have there was my first quick trial to do some kind of reinforcement learning. And what I found from that was it definitely requires a lot of very good training data, and you need to retrain it to iterate. So in the video that I have there, I only trained it on standing data, and then I decided to have it try to walk around. So it was decent results and didn't fall over, but it didn't have the performance that I wanted. And at that point, I would have to collect better data, retrain the network, go again. So this can also be tedious. So what I want to propose is there a way that we can take advantage of the strengths of each of these techniques, be able to take the generality and powerful, simple heuristics, be able to optimize your system in real time when the heuristics aren't enough, and then be able to learn from your experiences and make the controller better without requiring human input every time you want to improve. So this is the combined framework that I came up with during my time as a PhD student. It takes into account this offline heuristic design with parameter learning online. So the first thing that in this kind of orange square is this expert design for heuristics. And those can come from kind of common sense, being able to observe nature, seeing what animals do, seeing what other robots have done, analyzing the physics of your robot. And then the next one is this kind of offline learning where you're able to completely explore your cost space or put yourself in situations that you can't on a real robot when you're online, such as slowing down time and allowing your optimization to take as long as it wants. And then taking that data, doing some kind of data-driven analysis, whether it be reinforcement learning, statistical learning, any kind of inference technique. And you can kind of join those two together to put them on the robot. And then finally, there's always a difference between what you compute in simulation and what happens in the real world. Our models are never going to be perfect. They can be very good, but there's always some difference. So at that point, I apply this parameter learning to kind of take those heuristics that we found in the offline design and be able to adapt them online, change the values. But the stuff that we did offline gets us to at least a good enough region where the robot's not falling over and we don't have to learn from scratch. We're just making the controller better. So the first thing with RPC is it relies on the use of very simple models. So even though the mini cheetah robot that I'm showing there is a multi-degree of freedom system with legs, several degrees of freedom per leg. There's 3 on each one. I model it as just a single rigid body. So you have the center of mass position, orientation, and the derivatives. And the inputs to the controller are the footstep locations for each step and a force vector for the ground reaction forces. And this allows us to use very simplified discrete dynamics rather than using the full nonlinear dynamics of the robot. So we kind of jokingly call it the potato model because the robot basically just thinks it's a single potato floating in space with these force vectors that kind of push on the body, but the legs are massless and we don't actually consider the kinematics of the legs during the control. So what the algorithm actually is, it's a real-time nonlinear optimization, and the decision variables are both the future states and inputs over some prediction horizon. So at every single time step over your prediction horizon, you're optimizing for the optimal center of mass states and also footstep placements and ground reaction forces. And what separates this from traditional model predictive control is that rather than relying on a good model of the system, we try to exploit heuristics through regularization. So what do heuristics actually mean? I have this example of the robot trying to basically just stand in place and do a trot in place without any kind of regularization. Since it's a very nonlinear problem, we have all of these different local minima that the robot can be in. So you see the jumps between different steps. But we also know that the robot can place the feet under its hips, and that would be a good enough solution for being able to trot in place. So we can add this regularization cost. And when the two get added together, we get a smoother, still nonlinear cost function, but the behavior is much nicer. So that's the basic idea, is to make the optimization better without changing the optimal solution, but you do want to have it stop jumping from optima to optima. So like I said, the goal is to bias towards a good enough solution, but let the optimization search for a better solution if there is one available. In the case of trotting in place, a good enough solution is stepping under the hips, but say you want to go forward, and you're regularizing to just under the hips. As soon as you start moving, that no longer becomes a good example of regularization. The robot starts falling over and it's not able to get its foot where it needs to be. So an example of good regularization would be a state-dependent regularization heuristic, such as in this case, when we have a robot walking forward and backwards, the heuristic that we're actually using is the Rayburn heuristic, where you want to place the foot in the direction that you're walking half of your stance period, depending on your velocity. So now we have much better behavior, even though the underlying controller is exactly the same. If you have better inputs, you're going to have better outputs. So we were able to shape the cost function to make it solve faster and make it solve nicer, but we didn't change the actual optimal. So how do we design these good heuristics? Some ideas that have worked for me and that I think are good ideas would be to observe nature, things like place the foot in the direction that you're walking, analyzing the physics of the robot, things such as capture point, some data-driven analysis, take a look at what the optimization tends to choose and in which situations it chooses it. And maybe that's a good heuristic to kind of feed back and make the optimization stronger. And then finally, these learning methods of how to actually just come up with these heuristics from without needing any kind of intuition and just being able to let the robot figure it out on its own. So this is an example of how one of these data-driven methods would work. You basically would run some kind of exploration and you get this huge mess of data. This is the matrix that I'm showing there is a bunch of kind of correlations between different states, different combinations of states, states multiplied by other states, and that matrix can be huge. So what you want to do is try to fit some kind of model to it. If you want to train it on a neural network, if you want to just use a simple model, I tended to choose simple models during my PhD, simply because they were intuitive, and if something went wrong or if I wanted to change something for a future trial, it was very easy to just change one of the parameters rather than have to retrain or relearn the whole network. So in this case, we're fitting to a linear polynomial model, and we can look at one of these examples of a highly correlated data. So in this case, whenever the robot walked forward, it would tend to pitch down, and whenever the robot walked backwards, it would tend to pitch up. And this can be due to a number of reasons: poor swing leg tracking, incorrect model values for friction on each of the actuators. It can be due to any kind of inconsistencies. But the extraction framework was able to pick this out and find a model for it. So it finds this linear model that says, okay, we know that when you walk forward, you're going to be pitched down. So a heuristic would be when you're walking forward, try to pitch upwards so that in the end, you're level when you walk forward or you walk backwards. And then on top of that, you can estimate these complex dynamics. So we have this first order polynomial model, and then if you look at the first order polynomial model, it's not a very good fit. It follows the trend, but you have this kind of moving around the line. So what we were able to find is that there's this natural pitch dynamics that comes with the gait of the robot. So we found this sinusoidal relationship between gait phase and pitch. So when you combine these together, you get this complex combination of different heuristics that end up matching what actually happens to the robot. So I don't know if you can see very well, but on the graph on the right, we have a kind of darker red line, which is the heuristic that we're expecting for the robot. And then we have this orange line, which is the actual dynamics of the robot. And we were able to estimate them the actual dynamics just by using these two simple heuristics very well. And now we can compensate for these dynamics when we're actually controlling the robot. And so we can see how the robot improves as you add these heuristics. The two graphs that you see, the top one is the darker regions are where the robot's stable, the lighter regions are where the robot falls over. And the top one is forward velocity versus lateral velocity, so moving translationally. And the bottom one is forward velocity with turning rate. So either turning in place or moving forward and turning at the same time. So we see in the first video that the robot's kind of pitched down as it walks forward, and it doesn't really look as good as we want it to be. So the first heuristic that we found was kind of a linear heuristic with forward velocity and footstep placement, which said basically put your foot in the direction that you're walking. And we see how this viable region where the robot's stable kind of starts growing. The next one was a similar linear relationship with turning rate and footstep placement. So similar to the other one, place your foot in the direction that you're turning. And we see again that the viable operating region starts increasing. The final one was, or the second to last one that I found was a little more interesting. It was a linear relationship on the cross product of forward velocity and turning rate. So we can see how these interactions, as the robot's moving forward and it's also turning, the robot tends to put its foot outwards away from the center of the turn. And that kind of intuitively follows what you see in nature. If you see an animal running at very high speed and turning, you'll see it place its feet outwards along the radius of the turn. So it's cool to see that the heuristic extraction framework was able to find this all on its own. And then this final one is the heuristic that I talked about previously, which is the orientation heuristics with the different gait phases and the forward velocities. So if you look back at the first set of graphs versus the last set of graphs, you can see that even though the controller is exactly the same, all of the gains are the same, the areas where the robot's able to be stable and the amount of region that we're able to cover greatly increases just by giving it better heuristic inputs. So we can kind of see the results of this in different robust dynamic videos. So the first one is just a set of pushes where I basically have this stick and I'm just kind of beating the robot and pushing it in different ways. I definitely spent a lot of time during my PhD just like pushing on the robot and trying to figure out which were the failure cases, where was the robot not stable. And it ended up being a pretty stable robot in the end. I was able to go over rough terrain, able to go over unstable, hard, soft, slippery, pretty much anywhere that I sent it, it was able to walk over as long as its feet could get over the actual terrain. It was also pretty robust to model inaccuracies. So in this case, I'm telling it that the model of the robot is much smaller than the robot actually is, and it's able to walk around even with its feet very close to itself. As I mentioned before, it's independent of the actual kinematics of the robot. So I was able to flip the leg and the robot's able to walk around all the same as I pulled on the leg. It was also robust to drops from very high altitudes, or at least for the robot. This is over 4 times its body height. I was able to drop it and it's able to stay up and recover and be able to figure out how to reject the disturbance. And then another important thing that I worked on was the ability to not only withstand pushes during stance, but as it's moving, be able to mess with the legs, try to trip the robot, and have it still be able to go to its goal location. The goal for these robots is to be able to achieve some task autonomously, and you don't want to have to continuously monitor if, as the robot's walking, if it fell over, you have to go pick it up. You want the robot to be able to handle all of this. So we can see again the progress from the naive MPC, which is using no regularization heuristics, to just an initial guess with no regularization, adding some regularization but no extra heuristics, then adding in analytical heuristics, and then finally we're able to get the full dynamic capabilities of the robot. We were able to basically max out the torques and velocities on the robot, meaning that we were reaching the limits of the hardware rather than being limited by our controller, which is the goal for me as a control engineer, is to make the controller the best possible that it can be on the hardware that I have. So how do we take this and add it into, how do we add vision? How do we deal with different terrains? So far, everything that I've shown has been assuming 0 ground height, but we can use vision or some kind of local ground slope estimation to better inform the controller. And this is, again, very straightforward with the controller that I developed. You basically just have a constraint that used to say step on the 0 ground, and you can just give it some value at the XY location that you're expecting to touch down. And it's a very simple addition, a very simple modification, but the results are pretty apparent. So without estimation, you can see that the robot's expecting to put its foot under the actual slope. But this means that you constantly get early impulses that you're not expecting, and the back feet are constantly missing impulses that it doesn't want to have hit the ground, or it wants to have hit the ground already, but it misses the step. So by using this local ground slope estimation that basically takes the position of each of the feet and estimates the local slope, it can say, okay, we assume that the next footsteps are probably going to follow the slope, and we're able to get much smoother movement. By using the same technique with some kind of vision where you can see the stairs or any kind of object in front of it, you can simply give the controller that ground height at that value, and you don't violate any of the constraints, and you're able to be robust and smooth in your movements. So we can see that in practice as the robot walks up and down the slope. It wasn't able to do this very well before I made this modification, which is why I think it's an important one to talk about. And it's also important to note that it's not only in one direction, you're estimating the slope in 3D. So as the robot's turning on the slope, it's able to know if it should put its foot higher or lower, no matter if it's turning or walking forward or walking sideways. And it's also able to do this even during disturbances. So again, I'm pushing the robot on the slope, and it's able to figure out where to put its feet and be able to deal with it. And by adding this local ground estimation and integrating that with the controller, I didn't really see much of a performance difference between walking on like slopes versus flat ground. And this video is one of my favorite from the Mini Cheetah. It just shows how robust this controller actually is. You have the robot walking around on this platform, and it falls off, but it's able to actually stabilize itself and be able to continue walking. That fall is almost, I'd say, 75% of its body height, which if you think of yourself as a human randomly blindly stepping off 75% of your body height, you'd probably fall down. So I was pretty excited to see that the robot was able to robustly handle this. So the next question that I had was, can we use the RPC for other robots? Everything that I've shown so far has been for Mini Cheetah, and a lot of that work has been during my PhD and kind of during my postdoc after I finished my PhD. I've also shown some results on the MIT Cheetah 3, but those two robots are, they were designed to basically mirror each other. But can we use it for, say, a biped robot or a biped robot with non-point feet? Or what about a full humanoid model? So the question is basically, do all of these robots, can they be modeled as this kind of simple potato model and be able to be input into the RPC? Because that's essentially what the RPC requires, is just a single rigid body model and some description of what force it, or what footsteps and force generating end effectors are available to it. And so the answer is yes, but kind of, with a slight modification. First, I was curious to see if it would work on the mini cheetah with less than 4 feet. So the first one was, I basically disabled one of the feet in the optimization, and the robot was able to walk around on 3 feet, no problem. Didn't even have to change any gains. And then I was able to get it walking on 2 feet. And this was a little trickier. It took about a little less than an hour of tuning to get working. But that's really nothing, in my opinion, to go from a quadruped to the same robot as a biped by changing a couple gains, mostly due to stability issues of the feet wildly swinging around. But we were able to get both of these working very easily with the same exact framework that we were using for the quadruped version of the mini cheetah. So then, extending from the point feet of mini cheetah, how do we adapt it for something that has plane feet? It turns out it's also very simple, as long as the problem's managed correctly. As far as the optimization, it's the exact same nonlinear optimization. You just have to add basically an extra decision variable for the orientation of the foot and a designation for where on the foot the robot can actually generate force. So in this case, we have this sort of line plane foot. So I decided to give it a toe and a heel basically. And those end up being constrained together by this foot orientation heuristic and a simple measurement, or a simple distance between each of them. And so the difference here is that the simple single rigid body potato dynamics with multiple contacts, you just have an extra loop to calculate for each of the feet and each of the contacts on the feet. But in the end, you still end up with the same vector of forces and torques on the center of mass, which means you can take that result and input it directly into the optimization, and you can extend the same optimization that was used on mini cheetah to a humanoid, to a biped. Say you have 6 feet, any kind of feet. And so here are some of the results in simulation. The first one is basically just standard controlled walking of line foot biped that Optronic had designed previously, called Draco 2. And it was basically just a lower body biped. And it's able to walk around pretty stably. And we were also able to get it to do dynamic jogging. So I'm not giving it any kind of reference as far as commands of velocity commands, go forward or turn or anything like that. But I was basically just seeing if the controller was able to stabilize very dynamic gaits on multi-foot or multi-contact feet. So those were all simulation based. The next step is obviously how to get it onto the hardware. And real robots are difficult. They're difficult to work with. They're very different than simulation as far as the problems that you can encounter. And so I kind of want to step back and show the path that it took from the original idea of making a robot that can run like a cheetah to actually showing results on hardware for the mini cheetah. So the theoretical derivation for the controller took me about 6 months to kind of get the initial, this is how I expect the robot, or this is what I expect my controller to do. This is the math behind the controller. And then to get a proof of concept working, it was still under a year. It was still pretty simple, pretty quick. And finally, I had a full dynamic simulation in a little over a year, from original idea to deriving all of the theory for it, to being able to show this on a full dynamic simulation. Took a little over a year, which at that point, I guess I could have said, okay, I'm done with my PhD. It works, like, great. But I really wanted to show it on hardware. I wanted to have it working and be able to see the robot in real life and be able to test how dynamic it, or how robust it actually was. So I spent about another year developing the controller, finding the edge cases, making it better. And then about 2.5 years, I was able to get something on Cheetah 3, which was the predecessor to Mini Cheetah, kind of the larger version. And it was very simple. I could walk forward, backwards, turn, but I wasn't happy with it. It didn't turn as well as I wanted it to. Whenever I pushed it, I was nervous that it would fall. So that's when I came up with this heuristic extraction framework to figure out what are the best possible inputs that we can give the robot, how do we get it actually running around. And while this was going on, my lab mates were developing the Mini Cheetah robot and Mini Cheetah platform. And finally, about 4 years from when I started my PhD, I was able to get the original idea that took about 6 months to derive all the math for, finally working on the real robot. So if you think about the breakdown between that, about 30% of that time was working on theoretical work in simulation as far as being the end goal. I was able to show that the full dynamic simulation was able to stabilize the robot. And then the real challenge became putting that theoretical work and simulation work onto the real robot. Ran into problems like my controller's not fast enough. The gains need to be lowered because the hardware wasn't stable at the gains that I was originally using. So that's why I'm going to propose this simple biped platform that we've worked on over the last couple months. The Draco 2 model that I showed in simulation, jogging and running and walking, that was eventually supposed to become this kind of full humanoid model. But before that, I kind of wanted to take a step back and develop this simple biped robot that's a point-foot biped. It doesn't have extra limbs. It has very simple degrees of freedom. And the reason for that is that it's a simple robot and it's easy to use. Eventually, we want to move to a full humanoid that's capable of grabbing objects, opening doors, being able to go upstairs, everything. But the simple robots are also much cheaper to work with. You can iterate much faster. And again, the same controller works exactly the same as Mini Cheetah and Draco 2. And we can see this visualization of the point-foot biped walking forward. And you can see the predictions of different steps as it moves forward. And it's pretty stable. And that was pretty quick to get working, from going from the Draco 2 biped to this other biped. It took about a day of work to make sure everything was working. So the basic biped locomotion capabilities that I want to propose is what I consider the core of locomotion for a biped would be this forward, backwards walking, the ability to sidestep, turning, and finally disturbance rejection. So I consider these, if your robot's able to do this, I consider it able to do basic locomotion. Ideally, you would not have to change gains for any of these tests, and you would be able to go from one to the other. You would be able to walk forward and turn, or walk forward and turn at the same time, and be able to be pushed at the same time as well. So we can see now that the robot's built. There's high fidelity between the simulation and the robot, but there's something about working on the real robot that you can't just live in simulation world. As you move the robot around, you get a feel for how what the gains on the robot actually mean, what the data that you were looking at in simulation what that actually translates to in the real world. You hear the sounds, you see the actual movements. And so that's why I think real world testing is absolutely necessary, and it should be like being able to have a robot that fails, having a robot that falls over and is able to get right back up and be able to walk, I think is extremely valuable. So that's why we designed this simple biped. It was cheap and it's robust to falls. We added some of those pads not only for falls, but also because the same kind of stick that I used for Mini Cheetah, I would also kind of hit this robot, so we didn't want to damage it. So yeah, like I said, robots fall a lot. This robot's, which we call QDB for Quick Development Biped. It's built to be simple and robust, so you can quickly iterate. Even though the robot's gonna fall, you can just pick it right back up and have it do another test. So finally, after some weeks of testing, we're able to get this robot walking around. And it's a point-foot biped, which means it's a simple system, but it's also pretty difficult to control. The RPC on it runs at around 200 Hertz for the nonlinear optimization, and that runs in parallel to the main 1 kilohertz control loop for trajectory control, swing leg control, all of that other stuff that you need. And the reason I'm excited about this is, although this biped is not particularly useful, a successful implementation of the nonlinear controller on this robot means it's promising to be used on a more complex humanoid. And we have similar disturbances on this robot, and it's very robust. Like I said, I was poking it with a stick and hitting it, and it's able to balance itself. Which I personally found a little more impressive than on Mini Cheetah, just because it's a point-foot biped rather than a quadruped. If in the second video I'm hitting the swing feet, and if your swing foot isn't able to get to the location that you need to be, the robot's gonna fall over. But the controller was able to quickly adapt for all the disturbances on the swing feet. I was able to trip the robot and throw things at the feet. It's able to stabilize itself. I was even able to put things under the feet and kind of move them around as it was standing. So I was pretty excited about these results as far as having a biped robot able to use the same exact controller as Mini Cheetah and be able to have similar performance on the biped analogous, I guess. So the next steps for me and kind of Abtronic and moving forward to the future is that we have this simple platform that serves to quickly iterate core algorithms. So if we want to try a new algorithm, it's easy to put it onto this robot and say, okay, it works, doesn't work. And then we're building the humanoid that you see on the right, which is going to be able to manipulate its environment. It's going to be able to open doors, go upstairs. It's going to have perception. It's going to have all the things that you want. And which is really the goal. A lot of my my research is on dynamic locomotion, which I personally think is awesome, but eventually we don't just want the robot to be able to not fall when you hit it with a stick. We want it to actually do some task. We want it to go save somebody in a disaster response scenario, or be able to go into a dangerous environment that a human can't. So the next steps from there too would be to integrate perception and manipulation and be able to kind of have those coexist with the RPC algorithm, which was designed to be blind. The goal is to have the locomotion controller able to operate without perception or any kind of environment sensing, but to benefit from it if we do have access to it. So those are kind of the next steps. And thanks for listening. If there are any questions, be happy to answer any of them.
Great.
Thanks a lot, Gerald. Okay, as usual, so you can either ask your question directly by raising your hand and I calling your name and you ask it, or you can write down in the chat part. Okay, we have the first questions. Okay, the first question is, could you please explain the implemented yaw control for point foot robot?
So the yaw control, that's one of the, let's see, where do I have it? That's one of the states that are being controlled. So you are optimizing for it. And with the point foot biped, it's, you don't directly have access to yaw control in the way that you would with, say, a quadruped. But since this is a nonlinear optimization, you know that if you place the foot forward and push, and basically this interaction of this R cross F turn between foot placement and forces, you're able to get the robot to turn in yaw, especially because you have a predictive controller. So you know you can put yourself into an unstable position for one time step, knowing that in the future you're going to be in a stable position. So turning in yaw, even walking for a point foot biped is always unstable, but you know you're going to be able to stabilize or compensate in the next footstep. So I'm not sure if that necessarily answers your question. I don't have a good mathematical derivation for yaw control of the point foot biped, but since it is a state that you're controlling through your optimization and you have access to footstep placements and forces, you are able to control your yaw.
Okay, next question is from Ayusha.
Hey, hey, thanks for the great talk. You had one slide where you had these foot forces predictions. So I was just wondering if your MPC also are you predicting these forces through the MPC, and do you have the foot position as one of the decision variables in your MPC?
Yes. So that's why it's a nonlinear optimization. You're optimizing for both footstep locations and ground reaction forces. So what you see on the screen, the image to the right, you have at each of these kind of balls on what it would be the ground. You have this kind of like, say, the red or the blue ball, and that would be your footstep location. The line would be the foot orientation, and then the red vectors coming out of it are the ground reaction forces.
All right, got it. And I guess a follow-up question to that is, in that case, then do you have like these linear complementarity constraints for foot contacts and forces, or how are you doing the footstep planning? Is that, again, a Rayburn style heuristic, or is that something that the MPC?
So it mostly I don't have any kind of linear, any kind of constraints that would make it non-linear, but we have, I actually took that out, but I think it might have been important. But I have a slide that basically has all of the constraints, and there are very few constraints, things like no slip constraint, the foot isn't able to jump around once it's entered stance. But no, mostly the optimization figures all of that out on its own. No linearization or anything like that.
Or maybe the question should be, do you predefine the gate sequence and the timings?
Oh, yes. So as far as the gate sequence of touchdowns and liftoffs, that's predefined. It's kind of fluidly predefined. So we do speed up the gate as the robot starts to walk forward faster, and slow it down as the robot's more stable until we reach a standing speed, basically, and then the robot stops moving. And as you start running faster and faster, you want to have shorter stance periods, but the swing period stays the same. So yeah, the gate sequence going into the optimization is predefined at each optimization.
So that's why maybe you don't need this linear complementarity constraint.
Yeah.
All right. Thank you so much.
Thanks a lot. So the next question is PRC running on board on the MIT Cheetah platform?
So let's actually forward. So here in the middle, it was running onboard on the MIT Cheetah 3. On most of the videos that I showed, it's running tethered from a desktop, simply because the computer that we had on the original Mini Cheetah was just not powerful enough to run it. But then we got a man, I forget what the second computer was, but we were able to get the RPC running on Mini Cheetah completely untethered and on board on a slightly faster computer. The one that was on the original Mini Cheetah was basically like an Arduino powered computer. So with a slightly better computer, you're able to run this in real time. Although I will say that instead of getting the 200 hertz that we get on the desktop or on Cheetah 3, we were running it around 60 to 80 hertz, which is still plenty of recomputation to actually stabilize the robot. Anything above 20 hertz I found works for the Mini Cheetah.
Okay, then the second part of this question is, so should we include the cost of computation into the cost of transpose? And if yes, how do you think that we should do it?
Interesting. As far as a theoretical, should we do it? I personally don't have a strong opinion on it. I think however you can get your robot to walk. I don't think we're at the point yet to, like, once our robots stop falling, I think we can kind of have these more theoretical discussions of what constitutes good locomotion. I feel like a lot of my work currently is still focused on being able to get the robot to where it needs to be without falling over and then under some kind of disturbances. But I personally haven't done any kind of comparison between algorithms that are faster computationally versus less computationally, or that use more energetics or less energetics. I will say the video that I showed at the beginning of the learning controller was my attempt to reduce the computation that's actually running on board. Instead of having to solve this optimization problem, I tried to basically do imitation learning to get a neural network to replicate the results of my optimization without having to do that heavy computation.
I think I can also add something to your answer. Is it would be a bit difficult to incorporate this into model-based optimization because you need to come up with a model that's differentiable first to incorporate it. Yeah, it's difficult to come up with such a model. Okay, we have this next question. Based on your experience, what is the advantages of this nonlinear MPC scheme in comparison with the linear version based on the potato model?
So I found it to be very different, not necessarily in steady state behaviors. If you're walking forward or you're turning, if you're in normal operation, the convex MPC that we developed in my lab and the RPC, which was the bulk of my PhD, those two basically act the same. Where you really see it shine is under disturbances, which is why I tend to show a lot of disturbance videos and poking the robot and having it run off things. And the reason for that is the linear version isn't optimizing for footstep placements. So you're simply just either doing some kind of capture point or just stepping wherever the robot ends up stepping and trying to use forces to compensate for that. Whereas in the nonlinear version, you're optimizing for footsteps and forces. So you're able to say if you need more torque on your center of mass, instead of having to apply a ridiculous amount of force, you can just simply, the optimization would choose to step further out. So let's see, maybe I think there has to be a good video of, yeah, so in this pushes video that you see on the top left, I don't think we would not have been able to do that with the convex MPC. So here we're able to push it and throw it around. And you can see how the legs don't just fall under the hips, they kind of move outwards or inwards. And that was the real advantage that I personally saw.
Nice. Okay, I think I can go with the last question myself. So in this, the RPC that you were discussing, you show that you're adding some heuristic, or you're learning this heuristic, and you're adding it, and it improves the stability. While during the learning or extracting those, you didn't have any criteria on the stability. Isn't it by coincidence or by the choice of you that become useful for stability? I mean, it could be some weird motion that robots comes up with a weird tilt, or the motion of the legs. It actually helps for stability, and by trying to tune that out of it, it affects the stability.
Yeah, I completely agree with that. So the framework that I presented, as far as like this slide, that was just what I personally did for my PhD, because at that point, I was still basically trying to figure out the best way to get these heuristics. So adding a simple heuristic and seeing if it improved performance. So it would be the way that I was doing it at the time, and then seeing, is there another heuristic, and rerunning a test, maybe a different exploration. So definitely not the best way or the only way, but it was a way that worked and got the robot able to perform very well. The important thing for me is that the original framework, this one, it works regardless of whatever data-driven analysis technique you use. So I definitely didn't have a fully automated system. It wasn't choosing this heuristic is the best for stability. It just identified heuristics that were highly correlated. So whatever that means. If I ran a test for 100 seconds and I told the robot to move forward the entire time at a constant rate, it would find a some correlation between time and position, which is obviously a useless heuristic when you add it back to the optimization. So there's definitely work to be done there. I think a lot of that data-driven analysis can be replaced by some kind of learning method where you're rewarding some stability with some metric. I haven't personally done it, but that's definitely on my to-do list and something that I definitely considered. So yeah, absolutely right.